已解锁，请取出话筒。
OK，我们开始先。喂
Hello，
，Sorry，好，呀，对，
我这边最后处理停水的问题，就订了个酒店来度假了。
什么东西？
我说我北尔不是停水嘛，所以我后来订了个酒店来度假了。
OK，
所以今天 online 来上你的课。
好，OK。就这样罢了。平时可以成 Hello，哦，这平时只有那个11个吧？对呀，算了。Okay, so let's start first. Okay, so last time we talked about functors, right? So functor is a map from a category to the other category, okay, whereby you need to tell me where you want to send the object, and then you also need to tell me where you want to send the morphism. Okay, so to data here. So today we're going to talk about natural transformation, where you want to map between functor. So you want to map between functor. So this functor should go from the same source category to the target category. Okay. So let's take two covariant functor. Okay, so covariant functor just means that it will preserve the order of your map. Let's take two covariant functor, and then we have a natural transformation. Now from S to T. Okay, so this is a map between map. actually is a one parameter family of morphism in where, let me see, in T. Okay, so what does this mean here? So it means that so T here is defined for any C, okay, such that tau C should tell me where I send SC to TC. Okay, for C in the option, let me see. Okay, so you need to tell me map between maps, right? So, well, this map should add on some object. Okay, so I need to see where S go first. Okay, and then I tell you where to go to TC, how you go to TC. And then SC and TC is something in D, right? This is something. So altogether, I have a map in D. Okay. So then there's another property that this natural transformation have to satisfy, or sometimes we call it naturality. Okay, so that is if let's say I swap the C. Okay, so let's say I have a map from C to C prime. Okay, then this natural transformation will react naturally. So meaning this following diagram commute. So I can do tau C, right? I also can do tau C prime. Okay, but then there's also a map in between SC and TC. Okay, so we want all this map to commute with each other. Okay, because being a functor, you can send this morphism in C to a morphism in D. And so if I put all these together, I want it to commute. Okay. If this if because these are the morphism in D, right? So I can ask whether these morphism are invertible or not. Okay, if all of them are invertible, then this natural transformation is what we call a natural isomorphism. Okay. So in particular, in algebraic topology, there's one natural transformation which is a morphism from pi1 to h1. Okay, the abelianization of pi1 is a natural transformation. So meaning, if you have a morphism in space, then it will commute, okay, with this induced map. Okay, so let me write down. So a natural transformation, natural isomorphism, okay, is a natural transformation such that all tau C is an isomorphism. Okay. Maybe one example of natural transformation is the functor from pi1 to h1. Okay, ignore algebraic topology. Okay. So this is a abelianization. This one is a space of loop. And then the other one is, can think of it as a modules of Simplex. Or if you like, it's the building block of your topological space. Okay. Well, there's something you can prove here. So a composition of a natural transformation should be a natural transformation. Okay, so I think the non-trivial thing is the commutativity of the diagram, but then if you put two commutative diagrams together, the whole diagram should commute. Okay, and the other one is a natural transformation. Let me see. A natural transformation of x to t is a wait. Let me write down what this means. So it's a natural isomorphism if and only if there exists a natural transformation sigma from t to x with sigma tau equals to ws and tau sigma equals to wt, where ws is the identity natural transformation with the identity morphism. Okay, so meaning ws restrict to a, xa going to xa is actually the identity. This is this notation, right? I think we use this notation. Okay. Okay. So what do we have to do here? So if we have a natural transformation, that means if you apply to all the objects, each tau c is an isomorphism, so you can invert. But then here it says that it's equivalent to an existence of another natural transformation. Okay, such that the composition give you the identity natural transformation. So what's the natural identity transformation here? It is the identity morphism that when you apply to every object. So any idea on this proposition? So this, right, this give you every tau c is an isomorphism, right? So it means that there is a inverse for every tau c. Then you can use this inverse to define your natural transformation sigma here. Okay. And then at the same time, if there is a natural transformation that give you the inverse for tau, then the component morphism should give you the isomorphism for every tau c. Okay, because this ws being an identity morphism means what? Means that sigma a tau a should be equal to identity. Yeah. Okay. Yeah. So basically, a description on every component is just give you the natural transformation. Okay, so maybe since most of you are here, right? Maybe I want to add on a bit from last lecture. So last lecture, someone asked about the category of category, right? Okay, so in particular, how category theory solve the set of all set, right? So how it solve the set of all set is because we put all the set into a category, but then the category of set is not a set itself. So there's no paradox there. Okay. But then if you consider category of all categories again, then the category will satisfy the category definition, right? So you expect some similar paradox as Russell paradox, but then it's proved by this Lawrith, right? Okay. Lawrith, yeah, this guy. It's in 1969.
我可以问一下这边说他 proof 了啥吗？
I think it's very technical stuff. He proved the inconsistent of the theory of category, but I guess something related to Cartesian closed Cartesian category. Yeah, something will get wrong with products, terminal object and stuff like that. If you're interested, you can look for this guy. Yeah. Okay. Then I also add in the part that we talk about the essential injectivity, right? Yeah, I also add it in. Being fully faithful can give you some concept of essential injective. So meaning if fx isomorphic to fy, we will have x isomorphic to y. Okay. So feel free to ask questions when I go along this topics, right? Because as you know, these topics, right, you can read anywhere else, right? So if you have any problems, you can point out. And then we can try and discuss, or I can try and find it. Sometimes I will ask, but if I don't ask, please ask. Otherwise, it will be pretty boring. Yeah. Because this subject, right, is kind of abstract. Yeah, because it grew from a lot of topics actually, and mainly from algebraic topology. So if you have learned, it's better that you have learned algebraic topology first. Yeah, you will see where these things came from. But if not, there's no harm to learn from just abstracting. It's like you learn max, right? Like actually 1, 2, 3 is kind of abstract, right? So why this symbol like represent this idea of how many things? It's very abstract. So that's why many people actually can't catch up, even from kindergarten, but I guess primary school, secondary school, there will be people uh, left out from max because these symbols are very abstract. Okay, so partly why you can understand the concept is because you already understand some abstract thing, or you already see some concrete thing that you abstract the idea. But then the level of abstraction is different for every people. Okay. So maybe some people can reach to this stage, some people can reach to the different stage. Okay. But then I guess through learning, you can have a better level of abstraction. Sometimes this is closely related to maturity, how you think about things. Sometimes you stuck in some situation, right? It's just because that uh, you you still cannot figure out what's the mm, what's the how to say? I don't know. Do you know like why you get stuck for some time? Do you know why? 有想过自己为什么有时候会卡住？有想过 没有想过自己为什么会卡住？有吗？没想过？没想过？你觉得为什么？比如说，啊啊，你现在是跟我讲数学吧？是吧？哦，没有没有，我只是问你，我只问你吧。各种 style 其实啊，但是那时候应该没有很多 definition 哦，还是很多事情绕着你，可能 maybe 肯定有很多种 style。But then like but then yeah yeah，继续吧，就是一个。But then I mean 有很多原因啊，but then 我觉得应该是有一个，怎样讲，有一个点，比如说给你一个 example 啊，比如说一个水那个吸水盆啊，为什么会塞住？很多东西都可以塞住它，但是只有一个点可以让你塞住它。我的意思是这个，你找不找得到那个可以通的那个洞？还有很多东西可以塞住它，可能是什么软的，还是 sponge 啊什么不同的东西塞住它。当然你要用不同方法去解它了，but then 只有那个洞被你塞住，你们能找到那个洞？对，什么东西被塞了到底？Yeah. OK, so my point here is 这个洞就是那个 maturity，就是你 ability to attract the ability of being attract 那个 maturity，就是你能不能呢从这么多的原因里面跳脱出来？OK 吗？嗯，OK。Well, let me see. Let me see. What's the next thing I want to do? Okay, so finally we reach a very important lemma. Okay, it's very important lemma. In history, there's a lot of important theorem we call it lemma. Yeah, sometimes lemma is very important. So before introducing this lemma, let's talk about this notation first. So given two categories, right? We can define something called the functor category. Okay, so meaning functor form a category. So this functor category we will denote as bracket CD or D to the superscript C. This is a bit like the notation in set theory. Okay, the map from C to D. So the object here is just functor from C to D. And then the other one is morphism. Okay, so what is the morphism here? Map between functor, right? So what's the map between functor is the natural transformation. Okay. Sometimes oh, never mind. No, sometimes maybe not important. Okay. Okay. So now you can see a level of how to say hierarchy here, because object here is no longer category. Object here is functor. Okay, and then morphism is a map between functors. So what if I include another level here? So let's say, okay, maybe this one is a bit advanced stuff. So for example, I can consider the hierarchy here. I can consider objects being category, and then morphism is, let's say, functor, and then I can go to morphism, which is natural transformation. And then I can do similar thing to natural transformation. Okay, and so on. Morphism, and keep going on. Okay. So sometimes we will just call this as objects with a different level. Maybe this one is the one object. Okay, two object, three object like that. Maybe we'll call this a zero object, one object, and then two object, so on. Okay, so you can have infinity objects, okay, correspond to morphism, and then keep going on. And then we also have name for these object with morphism. So if you have 0 and 1 together, this is what we call the category, ordinary category. So if you have 0, 1, 2, we will call this a 2 category, and then so on. Okay, 3 category, 4 category, 5 category, 6 category. Okay. And then if you have infinitely many of them, then we'll have infinity category. Okay. So how do you think about these category? You should think of these category as a web, spider web. You understand? Spider web. So, well, 2 points, right? You can make string across, right? Okay, and then between these string, you also can make string again. Okay, and then between these two web, maybe you can create another web, then web between web. And then actually, this is very close to our reality, actually, right? Using algebra. Okay. It doesn't make sense. Does it make sense? Does it make sense to you? Okay, so a line you can think of a morphism between 2 points, and then the surface you can think of it as a morphism between 2 lines. For example, how do you build a square, for example? Okay, so you just like fill it in with all the lines. And then how you build a cube? So you just put a bunch of square together. Okay. Right. Okay, then after this notation here, so we're gonna introduce a very important lemma. Yoneda's lemma. So let's see be a category. And then let little c as an object of category C. And then let f be a covariant functor. Then there exists a natural transformation. Sorry, not just transformation, but an isomorphism between the form space here and this FC. So let's examine what this is doing here. So on one side, you have a functor category. Okay, so meaning you look at the space of functor from C to Z. Okay. So this two functor is what? One is given, one is F. Okay, F is the main character we want to see, and then we compare to this home functor here. Okay, homomorphism from an object to something is a functor. This is everyone agree on? So if I put in another object here, right? Okay, this home space here is a set. Yeah, it's a set. Okay. And then is it a functor? So if you have a map from D to D prime, okay, so you can induce a map from C to D and then C to D. You just post-compose, right? You have a map from C to D, and then you post-compose with a map from D to D prime, then you will have a map from C to D prime. Okay, and then this natural transformation tells you what? You can send this home here. You send this home here into object in, where is it? Set. Set. Object set. Everyone know how to read this notation? I'll see, yeah, let me see. You know how to read this? So what does the natural transformation do? You need to tell me. You need to tell me. See. So a natural transformation is a map between functor, right? So where's the functor here? Our functor natural transformation should go between two functor. Where is the two functor they want to go? So I guess this y here. I guess we already applied it on C, right? We check it on all the C. Let me see. What's the two functor that we consider here?
我可以问一下你卡在哪儿了吗？
再想一下那个，natural isomorphism 是 between 哪两个方的？嗯嗯，Did I get the statement wrong? Yoneda statement. Let me see. Maybe you understand what's this notation here. Oh, from C to C. Oh, okay. Okay, so what's this notation here? So tau C, right? I apply C to this two functor here. So mm, I got a map from home C to C and then to FC. Okay, and then what's the element that I pick up here in FC? Okay, so I just look at where the identity element here gets sent to. Okay, and then the claim here is this map is projective. Okay, meaning you need to show injectivity and surjectivity. And then this will involve all the functor property and natural transformation on tau itself.
所以左边的是哪个 functor？
左边
对啊，
是哪个 functor？想想左边，嗯，对，左边是哪个 I think 这个 functor 会不会是
哦，他就是把 C 送到那个 home space 的那个 functor。
把 C 送去 home space，就是这一个去掉的嘛？
对啊，
对，把这个去掉，我觉得应该是。So this y, right? Y on C, right? You can remove the C, and then this is the functor between these two. This is a natural transformation between F and this home of home blah blah to F. I mean, this is a bit like the double dual proof, right? Double dual, like double dual is isomorphic to the vector space itself. Okay, I think we won't prove these in class. I will put out the notes. So if this happens, right, then we will say that this functor is representable. A covariant F set F is representable if you can show that there is a C object C such that F is isomorphic to form of C to something. Okay. So we say that the covariant functor is representable if there is a object C such that you can realize your functor as a form of C to something.
来，给出你的 example。
Example? 有什么 example 呢？
有点 trivial 的。
trivial 的。trivial 的。想一下有没有什么 trivial example？想不到，还是我去找一找。
行。
Sometimes this object here, I would call it a representable object. Sorry. This functor we call it representable functor, and then this object should be a name. There's a name for this. Yeah, the object that can represent this functor here. Yeah. Yeah, such as yeah. 如果你说了那就可以 set 的话，but then 你还是要 fit 一个 functor right？应该不是每一个 functor 都是 representable。Because 我想想，因为你要考虑 like f of d，f of d 会不会是从一个 form of c d 来？你应该也是要 fix 一个 f 吧？因为不一定每个 f 都是 representable。对 ，and then this c have to work for all possible d. This c is fixed for each f. So meaning you don't look at f anymore, but then you fix a c and then you look at the homomorphism out from the c. Then can give you this f. 有吗？曾经有看过这样子。I mean a very easy or trivial 的 example 就很简单哦。Then 你就拿 f to be 这个 form of c 去一个东西，but then obviously 这种比较白痴一点的，我们要有一个比较单的，不像 home，but then 可以用 home 来表示它。I think 比较简单的是 I guess 有一个东西，比如说 ，what if this c is a initial object? Initial object of that category, and you do initial object. 看一下 initial object 可以做 object empty set 做不了什么东西。
为什么是 empty set？
不要紧啊，我回去找找看。哦，讲到这里，上次我们 start with 那个 scheme right？I think 我 fill up 那个 details。So last time I told you scheme is a for variant functor, right? But then if you know about scheme, usually it's a contravariant functor, but then depend on what how do you view scheme? Okay, so what's the functor like? What's the source or target category that you care about? But then for our case last time, right, we care about for last time, right, we care about commutative ring to a set. So actually what this do is in a plain non-categorical language, right? What we did was, for example, we look at, let's say, R of xy, portion it out by, let's say, x plus y, and then we are just looking at the zero set of x plus y, something like that. Okay, so what's the zero set of x plus y? This is just y equals to minus x, right? So y equals to minus x is this line here. Okay, so give you a variety, algebraic variety. 你们有没有学到这边？有没有 algebraic geometry？有人学到这个吗？没有呗，zero set 有吗？是 zero set， but then 没有学 function， 没有 function ring， 没有，所以你们学到哪里啊？algebraic variety 我没有讲学 scheme 啦，but then like 这个coordinate ring 有学吗？有哈，对不对？所以这个就是 scheme 的 idea。I give you a coordinate ring and then you produce me a zero set. Okay. Yeah. So, but how do we view this zero set? There's a very advanced way to view it. Actually, you look at the form from spec R to X. And spec R to X. Then this spec R to X, right, will help you to read out these points. This is a modern way to see zero set. If you see it before, then you see it before. If not, you just take my word. Then, yeah. Okay. Actually, the idea of spec to this space, right, is not how to say. It's not strange to you also, actually. It's not strange to you. Maybe I can give you one example. For example, spec Z. What is spec Z? Spec Z are the prime ideal inside Z. So what are the prime ideal? Because Z is a principal ideal domain, right? So what are the prime ideal here? So exactly the ideal generated by prime numbers. But then you can realize that actually these, right, have a one-to-one correspondent to your number lines. Then let me see. Yeah. Yeah. So yeah, okay. Okay. Yeah, if let me know if you have any problems after you read this stuff. I can try and fill in as many as you want. But for now, just let you see the structure of things. Okay. Any problem? Any question? Up to here. So these are about functors or natural transformation. Later on, we'll go back to homological algebra where we'll discuss again kernel, co-kernel, stuff like that. Okay, in the most general sense of most abstract sense. And then kind of repeating what we did for group rings and modules. Okay, let's take a break until 9:05.
在想啥？
嗯，
我说你在想什么？看你一直盯着屏幕在看。
我在看找东西。 Yeah.
是离子的。
Englishman.
这个它是洛克的，small object 还是 one space 是个 set，其中一个是一个 set，然后这边有它的莫非那个 notation 呢？这个是 one space 的 notation，因为它的 one space 是个 set。
这我也找不这里的。
对，OK，所以就是说，换从一个东西出去看，或者说手另外一边是这个是它的方标啊，就是可能是那种不一样的标准。哦哦哦呀，是，OK，我大概懂了。哦，他是把这个符号，他把这一 side 的符号变成这个
啊什么？
这个 C 去这个它的符号。OK，可以，我们可以
我怎么
讲这个。
从来没见过这个符号？
有吧，有吧，应该有。So yeah, so I think 是语来讲一个 example is if you consider identity functor, right? Then this is isomorphic to form of C. I guess in that case, they are considering covariant functor. So not covariant, actually covariant. Okay. So C here is just the what's that? C 要放什么？要放 initial object 吗还是 C 是放什么 initial object？一啊，那一是什么
One element。
？One element set。哦，OK，sure。Yeah，它的 initial object 就是随便一个去到这个 identity functor。
为什么是
identity
non
functor 说它的 C 是 set 啊，是吗？还是它是 locally？哦，locally 是哦。它的这个 set 是什么？它这个 C 是什么？
对，
那
是
个
set。
source target set to set OK yeah sure set to set OK
应该没有查过这个 set 有没有 x，消息的。
哦有没有这个 x 哦yeah 不用了其实不用 OK but then I think I want to like point out from your maybe from your lower form of max right I think 你们应该有看过 like form of let's say field form of v 这个你应该看过吧？这看过吗？What is this？对对对，没有错。I mean like yeah，对，没有错。So this you can imagine as a functor as well, because why then? You can input any vector and then give you a dual space, right? Okay, but then this become your the object that represent your functor. But then you can see that this what do you say? This position is different, right? Because this dual functor here is a contravariant functor, so that's why your object become in the second space. 是不是有名字啊？Tom 有没有叫这个 object 名字啊？我记得这个有一个名字的哦。
哪个名哪个？
这个 object 有没有名字啊？Object that can represent a functor
我记得就叫 representing functor。
没有名字咩？Any name for the object that represent functor. Or representing object 就这样吧。Representing object. So this field is the representing object for your dual functor here. Okay. I think 还有一个是我们比较近期看到的东西，就是so maybe 我们还有看过一个 home，我们可以从 home 的那个方向去想。Let's say home of R to something. Okay. Maybe is a R module 啊。这个 home 可以做吗？记得吗 ？This home, what does this home do 啊？ This home actually is all the function, okay? But then this function is characterized by where you send the one. If you know where you send the one to, then basically you know how the function get defined because it's a module. Okay, so what does this mean? This means that every function here can read out the element in your M. Okay, and then what does this mean here? So what's the functor you can write down here? Well, you can just use forgetting functor or forgetful functor. Okay, so you just remember it as a set of things. This is like the example that Tom gave just now, C mentioned. Right? Yeah. Okay. So what I want to tell you that this thing actually is something that you've seen before, but then you maybe never think of it like that before. Okay. Yeah. So maybe you can recall, see where you've seen this kind of construction before, and then you think, is there a functor that can relate to this home? Okay, so let's continue.
Okay, so before we go delve into the homological algebra, so something to think about is category might not have initial or final object. Okay? Even if they have, they may not be the same object. Okay, like in the set. And a product co-product might not exist. Okay, for example, if you look at this category here, what category is this? Finite dimensional vector space, is it?
不是 field 吗？
Oh, sorry, field. Okay, I think I should write it. 看到一个 F restrict to D 是什么情况？
你是不是想写 FELD？
写一下看，不然的话不知道在做什么，讲错东西了。Okay, so if you take like F2 cross F2, right? So what's the characteristic have to be? F2 cross F2 meaning the characteristic to field. Okay, we cross that together. What would the characteristic be? And then kernel and co-kernel might not even make sense sometimes. Okay, if they make sense, they might not exist. So for example, kernel do not necessarily exist in the category of finitely generated module over ring. Because inside a finitely generated modules, you can find something that's not finitely generated. Okay, I think this one we've seen it before, but when we discuss about the Hilbert basis stuff. Right? So even when they are kernels and co-kernel, okay, more monomorphism might not be kernel. And epimorphism might not be co-kernel. Okay. And then amorphism may not be, maybe monomorphism. And so amorphism can be both monomorphism and epimorphism, but not isomorphism. Anything to comment here? Non-normal subgroup are not kernel. Because sometimes your monomorphism give you non-normal subgroup, right? Then they are not kernel. And epimorphism need not be co-kernel. So meaning this injection is not a co-kernel. So to have this nice property, right? We invent a category called abelian category. Okay, that we want the co-kernel and kernel to exist, and then there are the monomorphism and epimorphism. But before that, we need to have the existence of kernel and co-kernel first. So we will make something called the additive category. Okay, so to have all these nice property, right? So let's first define something called the additive category. Okay, so finally, I think we formally introduced this zero object. I think we mentioned it way long before. Okay, so zero object here is both initial and final. Okay, so here we make initial object and final object the same. Okay, and then we call it zero object. And then should have a finite product and co-product. Okay, so maybe I list them out. It's easier to read. First property is it has a zero object. This is both initial and final. And then second is it has both finite product and co-product. And then third, the home space is an abelian group. Okay, such that the composition map are bilinear. Okay, so here maybe you can give some examples and non-examples here. For example, group, okay, is actually not an additive category. Why? Why group is not additive? Which rule it violates? Not an additive category. Huh? Which one? Third one. Okay, so the home space might not be abelian, right? Okay, because the group itself is already not abelian. Okay. But then what can be a additive category? So for example, the category of R modules. Okay, category of R modules. By the way, there are two notations for R modules. I think one of them is R small mod. Where this one is for finitely generated. Later we will encounter this finite. 怎么忽然间 finite 不能这样写去 finite
NRT
这样子啊 OK Okay, this is additive category. It's additive. Okay. Then we'll define kernel, okay, in the most abstract sense for now. So let phi be a morphism in the additive category C. Then a kernel here is no longer some objects or what, is a map. Okay, so let's call this map from K to C. It's something going into the source. Okay. It's a kernel. Okay, so kernel still is a kernel of a map. Okay, if the composition, so maybe 2 points. 1 point is the composition need to be 0. You can think of it as an inclusion. That's why I put a iota here. And the other one is the universal property. Okay, so for all other map, also from somewhere into C, such that you can make the composition 0. Okay, then there should be a unique map going from Z to K such that the following diagram commute. Okay, so if you compose this to be 0, then it has to factor through this iota here. Okay, so one way to think about this K is like, this K is the largest object, okay, that you can put into C such that phi iota is 0. You can think of it as the largest. Yeah. 这样想，我觉得可以啊。对吧？可以这样想吗？想 kernel 这个 map，其他可以让它变零的，应该都是活在这个 kernel 里面。Right. Maybe you can think of this as the largest largest object that you evaluate using. 好，方向很重要，我这个方向。Okay, then after that, we can define co-kernel. Okay, so a morphism I B to A. Okay, so this one is going up from the target lah. Is a co-kernel phi if two things happens. So first is you do phi, you do pi, and then you get 0. And then for everything else that can satisfy the similar property, right? Okay, let's decide the direction. Such that beta phi equals 0. There should be a unique beta. Let's decide this. So you got C to B, right? Okay, so this is your phi. And then your B to somewhere else, Z. Okay, and then this composition is 0. And then at the same time, you have this B going to A, where A is your B to A is your co-kernel. Okay. And then you want to make this diagram commute. So how to commute? Well, this vector factors through this pi here. So there's a unique beta bar going from A to Z. Okay, so how to think about this? How to make sense of this? So last time you define co-kernel of certain map by what? By the image, no, not image, by the codomain mod out by the image of the map, right? Image of the map, yeah. 我想想 is that right? Oh yeah, that's right. Because only then your image will become 0. Okay, only then your image will become 0. So 想要这个可以这样解释。How to make sense of this commutative value? How do you remember this arrow? Like, 想知道不是往上走还是往下走？ How to make sense of it? I think to make sense of it is you want this to be true, right? You need to kill at least the image of one. At least 至少你都要把这个东西出去。Right? Yeah. Then I guess this beta here would send maybe a bit more than 5. I mean, 可以这样讲，我猜。Yeah, because this just says that beta composed with 5 is 0, right? But then what you can do is beta is a 0 map. Beta could be just a 0 map. then you set everything to 0. Obviously, you compose with phi also go to 0. Okay. But then the co-kernel here must at least send the image of phi to 0. Okay, then you will have a map from this A to Z here, such that this thing commute. So this thing commute means this thing. So this pi here, or pi here is the whole. So B is fixed actually. And this time to 0, and then this to be. So let's say we use the old method to think about this. And maybe this thing doesn't make sense in this category, but maybe it can help us to think about. Maybe I said previously. Okay, might not make sense in any category. So I mean, this quotient here might not make sense. But then maybe it should help us to think about this universal property. So I claim that this A, right, should be at least quotient by the image of phi. Okay, so that you have this pi, both phi here, where everything that's coming from phi set to. Okay, and then this beta here potentially will send more things to 0. More things. Okay, even before compose with phi. Okay, and then the claim here is there should be a commutative diagram here. Does this make sense? So what should this beta bar be? I mean, from previous, what you did was you just look at the representative, right? And then say that it's determined by this beta. So why do you have to cycle through this at least? Yeah, I think because if you gonna send more things to 0, so meaning what? Meaning after this pi, right? After this pi, what the extra thing have to go? The extra thing have to go obviously depend on this beta, and then this beta says that go to 0 first, so you have to go to 0 first. If it doesn't go to 0, if you go to something else, yeah, kind of fixed by this beta. How to think about this beta? Should be unique. I mean, for this kernel, right, I would think of it as an inclusion. Kind of inclusion. But then how about this one? Think about this. This should be some form of quotient, actually. But some form of quotient. Further quotient, I would say. Further quotient. Maybe you quotient more than the image of phi. Okay, anyway. Maybe let's see more, then maybe we have more ideas. Okay, so then these two are closely related to two concepts. Okay, so one concept is monomorphism. Okay, last time we see monomorphism as a limit, right? Limit of some diagram, some category. So a morphism is a monomorphism if for every C1, C2, okay, from Z to A, and then composed with phi. Okay, so maybe here I change to A, B, okay, and phi composed with C1 equals to phi composed with C2 implies that C1 equals to C2. Okay, I think this one we talked about it before. Similarly, if morphism phi from A to B is an epimorphism, if for all parallel map, let's say beta 1, beta 2 from B to Z, beta 1 compose phi equals to beta 2 compose phi, implies that beta 1. Okay. So you can see that monomorphism, epimorphism, right, is kind of imitating the left inverse, right inverse identity.
这个 definition 跟之前那个有什么区别？
没有差别，一样的。
好吧。
之前讲过是一样的 ，yeah. So, but then I didn't explicitly tell you about the left inverse and right inverse. So meaning left right inverse maybe doesn't exist. But then this is kind of like middle ground between element-wise definition and the function definition. Okay. I didn't tell you how you get rid of phi, but then if you have this property, it's an epimorphism. Okay, I didn't tell you how to get rid of phi, but then if the morphism on the right is equal, then it is a monomorphism. If it is on the left, it is equal, it's a epimorphism. Okay. Yeah. Okay. Okay. So in this case here, there's a lemma. So a morphism is a monomorphism if and only if for every C from Z to A, phi of C equals 0 implies C equals 0. Okay. And then morphism is an epimorphism if and only if for all beta from B to Z, beta on phi equals 0 implies beta equals 0. Okay. I guess this is very similar to the injectivity you see in groups or function even. Okay. So two ways to define injective function, right? Fxi equals to fx2 implies x1 equals to x2. Or you can check that fx equals 0 implies that x equals 0. Okay, so this is the same. Okay, so this is the same. So sometimes I think in Tom, maybe so you can check. Maybe in Tom, they define this to be monic, and then this property to be epic. I think epic, yeah. Monic and epic. Is it? Right? Okay, yeah. So there are three kind of idea here: monomorphism, monic, and injective. Okay. Okay. maybe next thing is worth to see the proof. So maybe next lemma. So in any additive category, kernels are the monomorphism, and co-kernel are the epimorphism. Okay, so these ideas get linked together. All right, so we just show one of them. The other one you could try yourself. So let's do it for the co-kernel one. Okay, let's do for co-kernel. So we'll show that the co-kernel is an epimorphism. So let phi be a morphism in C, and then let co-kernel to be a map from B to A. Okay, that satisfies the property that we mentioned before. Okay, so we want to show that co-kernel are epimorphism, right? So meaning what? Meaning you apply the equivalent definition here. So meaning I need to consider a map, let's say gamma from A to Z, a morphism such that gamma, let me check. Yeah, gamma on this co-kernel phi to be 0. We want to show that actually gamma is 0. Okay, by the lemma we had just now. Okay, so let's write down the commutative diagram we had. Okay, so we had what? Let's draw. Okay, so let's draw it. So we got C to B and then B to A, right? So here's co-kernel of phi, and then here's phi. And then we got A to Z. And then we know that this part composed to 0. Okay. I guess for sure we need to use the co-kernel property. Okay. So this part composed to 0, right? Also implies that the whole part here composed to 0. Okay. Okay, what's the co-kernel property here? What's the co-kernel property here? What's the co-kernel property here? Okay, so co-kernel property says what? Okay. So if you have another map from B to Z, okay, such that gamma of this thing is 0, then this co-kernel here will factor here. Okay. So in our case, what happens here? Where is the factorization happening? Where's the factorization happening here? Maybe I draw this 0 downstairs. Where's the factorization happening here? The factorization happening when you go out from co-kernel. Where's my co-kernel here? B to A, right? Okay, so there should be a factorization here. There is this a unique, what do we call it? A 0 bar, because this is our beta in this case. Okay. Okay. So then what's this 0 bar here? What's the map we can put here? Huh? Gamma. Gamma is the one that that the question give, right? Okay, but then by the co-kernel property, what this gamma can be? Well, I mean this because this beta is 0, right? So what's the unique map you can have here? You just put 0 here. But then the co-kernel universal property says what? The map between A and Z should be unique. There is a unique map between these two. And then you pick a gamma that's between this, that make this work. So this means that by uniqueness or by universal property, of by universal property of co-kernel phi, gamma have to be 0. Okay. Yep. Okay, maybe last one before we end. Lemma. Phi is a monomorphism if and only if 0 to A is X kernel. And then phi is a epimorphism if and only if beta to 0 is X co-kernel. Okay. So if once we establish this, then this is very similar to what we know about injective map. Because if it is injective, if a map is injective, then the kernel should be 0, right? If it is surjective, then the co-kernel should be 0 because your image can reach everything. So then this will be very similar to what we have. So 5 minutes. Can we do this? Maybe we can quickly do this. So proof. Let's prove for the case of kernel. Okay, let's prove for the kernel case. For the monomorphism case. Epi is similar. Okay, so let's go this direction here. Okay, assume mono and then prove this is a kernel. Well, to prove something is a kernel, right? So what do you have to do? Okay, so you got a map from, let's say this is A to B. So that's why it makes sense. Okay, so if you have another map, okay, that map to A, call it C, such that this is 0. Okay, we want to show that 0 to A is a kernel. So meaning what? I want to show that there's a unique map that do this. Okay, so because it is mono, right? Mono means what? If phi of C is 0, this will imply that C is 0. Okay, so this is 0 by monomorphism. Okay, but then if this is 0, what does this mean? My previous lemma, 之前的 lemma， 叮叮叮叮叮叮。If this is 0, then we claim that this curse will factorize uniquely through this 0, because this we just put it at 0, right? Okay, because curse is already 0. So it factors through a map from 0 to A. It factors through this 0 object. Does it make sense? Does it make sense? Does it make sense? Because Z is 0 by monomorphism, and then how can the map factors through? And this unique map here is just a 0 map. Does it make sense? Yeah. Y Z to B is a 0. Okay, very good. So if we want to show something is a kernel, right? Okay, so you need to take anything that composed with 5 to be 0 first. Because kernel is the thing that you compose with 5, you get 0. Yeah. Okay, so this is the condition when you want to show something is a kernel. And then second condition is you want to show that it factors through this kernel such that there's a unique map going from Z to this kernel. And then what this unique map has to be, it has to be 0 because this curse is always 0 by monomorphism. Yeah. Same. I think you cannot put a non-zero map here, right? Because your curse is already 0. Send everything to 0 already. Does it make sense? Because your curse is a 0 map. So it only can factors through 0. You can't be non-zero here. To be unique, because this is the one way to do it. Okay. Okay, how about the other direction? Okay, so how about the other direction? Assume you have the kernel picture. Okay, assume you have this kernel picture here. Okay, then how do you want to show that this curse here is always 0? Okay, how to show that the curse there is always 0? Okay, so maybe you should think about this unique map. What this map could be if this is the kernel. Opposite way to think. Just now we think from 0 implies this 0, right? How about here? If this unique map have to be 0, And what's the original map has to be? I think there's only one map you can put, right? Anything equal to 0 is a 0 map. So what's this cursive map have to be? So this map composed together, what is it? 0. But this thing commute, right? So it implies that C is 0. 就是这样嘛。Yeah，就这样嘛。0 to A I think 是那个 obvious map 吧，就是 send 0 to where？ 这个 0 I think 是那个 initial object， 呀，说它是有一个 unique 的一个 map。这个 0 是那个 0 object。Yeah. 0 object。那个 0 东西是那个 0 object。现在有没有什么东西 miss 掉？有问题啊？呀，有问题吗？什么东西 miss 掉啊？呀，什么？上一个，这个我们要 prove that 它是个可能。对，啊，你的意思是说，我如果 compose 这个 map 去到 B 是 0，因为这个 map 应该是 0嘛，对不对？这个 map 应该是 0。哦，这个是 0，你要 check，这个是 0，你要 check，and then 第二个是你要说，这个是第一个点，第二个点是你要说这个 universal property 啊，这两个点。如果有其他的 act like a kernel 的东西，它就要 factor through 这个可能。这是第二个点。第一个点确实是要 compose 去 and then 还是零。这个 map 应该是这个 unit map，就是那个零 map。这个 unit map 是那个零 map。OK，然后另外一个方向就是假设我有这个 universal property，这个是一个零 map，这个是一个零 map，然后这个合在一起是零 again，然后我用另外一个零 map，and 这个是什么来着？反正这个东西要 factor through 这个 map，所以是说这边要 commute，反正这边要 commute 的话是什么？这个方向是0，0，这个方向是 OK。 所以就是一直转方向在讨论这个 commutativity 的东西，然后用 uniqueness 哦，因为零这个东西蛮 unique 的，就是你有一个 natural 的 zero map，其他 non-zero map 可能有不同的做法，所以有比较多可能性。But then every zero map then 就一个可能性。OK OK 吗？Okay, if no problem, then 我们下次 start with abelian category. OK，
下课了。
下课了。